This is Lesson 8 in Module 8. The topic of this lesson is subnets and software-defined networking. After completing this lesson, students should be able to explain the reasons that we may want to split a network into subnets and how this might be done, calculate a subnet mask, network address, and broadcast address, and describe what software-defined networking is and how it works.
Here is a diagram showing the IPv4 address scheme. The 32-bit address space is broken into 4 octets, with each octet converted to a decimal number, leading to a 4-number dotted decimal address as shown. The addresses are divided into 5 classes, A through E. An organization can be assigned a block of addresses in one of these classes depending on the number of individual addresses the organization requires. For example, a Class A block will allow for 16 million addresses, which means this class is not going to be assigned to too many organizations. A Class B network will provide 64,000 addresses, and a Class C network will provide 254 hosts.
An IP address has 2 parts. The network address, which is the first part of the address and points to the network's unique identifier, and the host address, which is the second part of the address and points to the host or individual device identifier on the network. As mentioned before, an IPv4 address consists of 32 bits. Each string of numbers is separated by a period and consists of 8 bits. This means that each set of numbers includes the range of 0 to 255. Organizations could purchase 3 classes of IPv4 addresses from the list of Class A through Class E. A Class A address has 8 network prefix bits. A Class B address has 16 network prefix bits. A Class C IPv4 address has 24 network prefix bits. Class D is designed for multicast addressing, and Class E is reserved for future use. This scheme is referred to as a class-full address scheme. Here is a list of IPv4 classes I borrowed from Wikipedia. The important items to note on this are the network bits, indicated by the use of an N, and the host bits, which are indicated by the use of an H. These are the 2 parts of the IP address we need to be aware of. Segregation is a method to split up your address space into logical subnets or enclaves. This is a way to divide an organization's network into a smaller number of systems that can isolate groups of devices for specific functions and individuals. For example, a network for R&D may be separated from the larger corporate network and made available only to researchers. There are also security benefits of splitting a network up in this way, as it allows for additional security for each of the subnets so that if an attacker gains access to the corporate network, access to subnets and the data it contains can still be protected.
Enclaves are sections of the network logically isolated using networking protocols. In this diagram, we see 3 enclaves, or segments, of the network that are separated from the others, but that are reachable from the WANs.
There are a number of reasons that you might be interested in dividing your network into subnets. First, remember how a broadcast packet will reach every device connected to your network, even if it doesn't apply to that device. This can put a strain on the network if multiple broadcast packets are sent. Subnetting will allow you to limit the number of systems on the subnet, which means fewer packets being broadcast on the network, which can slow the network down. Second, going hand in hand with the first reason, with a smaller number of systems on the subnet, this will ensure that a higher percentage of traffic will be destined on the average for each system on the network or the subnet, reducing congestion. Third, subnetting can improve network security as it is easier to monitor a small number of systems rather than a large number. Additionally, systems that have a greater need for security based on what their mission is can be separated into a subnet where additional security controls and devices can be utilized. Fourth, organizing your devices into smaller, logical collections of systems allows you to grow the network in a more organized manner, controlling the network as it grows. There are also ways to organize subnets so that they can include more devices by using other network devices. Finally, fifth, organizing the network into logical subnets can ease the overall administration and management of the network. The 32-bit IPv4 address consists of two parts. These are the network address and the host address. The number of bits in each part of this address scheme will depend on the class of the network and the organization's assigned network address. What we are going to do when we employ subnetting is to take the organization's host address and divide the bits used for this portion of the address into two parts, the subnet bits and the new number of host bits. This method of dividing networks into subnets and possibly subsequently dividing subnets into further subnets is known as variable length subnet masking, or VLSM. One final comment we need to make is that there are, in general, actually only 254 possible host numbers instead of 256. This is because 0 is used for the network address and 255 is used for the network broadcast address.
One way to extend the number of devices that can be communicating across the internet is to obtain a NAT-capable device. A network address translation device, or NAT device, is assigned one of the organization's IP addresses. Systems will send packets bound for the internet to the NAT device, which will take the internal address for the system and replace it with the NAT device's IP addresses. It keeps track of all packets that it sends out this way, so that if a response is received, it again translates the address so that the destination would now be that of the original system. This results in a much larger number of internal systems that can still access the internet. The internal network assignment of addresses often uses the 10.x.x.x range. In terms of security, the NAT device somewhat obscures the internal network from outside individuals, since it replaces all internal addresses with a single IP address for the organization. Another topic associated with the IP address space is that of subnet masks. A subnet mask is a 32-bit number created by setting host bits to all zeros and setting network bits to all ones. In this way, the subnet mask separates the IP address into the network and host addresses. The 255 address is always assigned to a broadcast address, and the 0 address is always assigned to a network address. Neither can be assigned to hosts, as they are reserved for these special purposes. When organizations need additional subnetworking, subnetting divides the host element of the IP address further into a subnet. The goal of the subnet masks are simply to enable the subnetting process. The phrase mask is applied because the subnet mask essentially uses its own 32-bit number to mask the IP address. The Class B network shown has 5 bits assigned to the subnet ID and 11 bits left for the host ID. To create the subnet mask, we fill in a 32-bit number with 1 for each network ID and subnet ID bit, and 0 for each host ID bit. We can then convert this to dotted decimal.
VLSM is the variable length subnet mask, and it is in essence creating subnets of subnets. It is a method to help subdivide the class-full IP addressing. CIDR, or CIDR, is classless interdomain routing. It implements a method for IP addresses independent from the traditional IP classes method seen in class-full. CIDR utilizes IP addresses without classes. CIDR uses a notation of /XX, where XX is the number of masking bits. So, for example, 192.168.5.85/24 tells us that for this IP address there are 24 masking bits for the network address, leaving 8 bits for the host address. Let's look at an example. Let's say we have an IP address of 192.168.5.85 and are told the subnet mask is 255.255.255.0. If we look at the binary equivalent of the 255.255.255.0 subnet mask, we would get the values as shown here. Thus, we can see that the first 3 octets make up the network address of 192.168.5, and the host address is 85, contained in the last octet. Let's look at another example. This time, let's start with the CIDR representation of 10.128.240.50/30. The IP address we are looking at is thus 10.128.240.50. We see from the CIDR notation that the subnet mask has 30 bits, so this gives us the binary subnet mask that is shown. Remember that the /30 tells us that we are using 30 bits for this subnet mask. This will result in the dotted decimal notation of 255.255.255.252. We arrive at the 252 number by adding up the value of each location where there is a 1 in the octet. Thus, 128 plus 64 plus 32 plus 16 plus 8 plus 4, which equals 252. Remember from before when we said that the network address is 0 and the broadcast address is 255? Well, we can't use these values now because our subnet doesn't consist of a full 8 bits worth of hosts. To determine the correct network and broadcast addresses, we need to convert the IP address to its binary equivalent, resulting in this value. We then take the subnet mask we determined before, then we AND the 2 addresses together, obtaining the result shown. Remember that with an AND function, both values have to be a 1 for the result to be a 1, as shown here where we highlight one example of each possible AND calculation. We now know what the network address is. It is the result of the AND function, which in dotted decimal notation is 10.128.240.48. This is conceptually equivalent to the 0 network address we looked at for the classful scheme. We still need the network's broadcast address. To determine this, we set all of the host bits to 1. From the subnet mask, we can see that there are only 2 bits for the host, So we take the network address and set the two host bits to 1. This looks like the following. This then provides us the broadcast address in dotted decimal value of 10.128.240.51. With only 2 bits for the hosts and with 00 taken up by the network address and 11 by the broadcast address, this leaves us with only 2 addresses we can use for our hosts. The addresses ending in 01 and 10. This means the only 2 possible addresses for hosts in this example are 10.128.240.49 and 10.128.240.50. Let's take a look at the effects of network masking. Let's compare the 2 CIDR described networks as shown on this slide. In the first example, there are 24 bits used for the subnet mask, which means that we have 8 bits for the host addresses. In the second, we have 28 bits for the subnet mask, leaving only 4 bits for the host addresses. After subtracting the network address and the broadcast address from each of these means we will have 254 and 14 possible host addresses for the networks respectively. The network and broadcast addresses can be calculated for both fairly easily in this case. For the first CIDR address, we would have all zeros for the host bits, resulting in a network address of 10.128.240.0. For the broadcast address, all bits would be set to 0, so the broadcast address would be 10.128.240.255. For the second network, the 4 host bits would again be all set to zeros, yielding a network address of 10.128.240.0, just like the first network. The broadcast network, however, would be different since there are only 4 bits for the host, and all 4 would be set to 1s, and the resulting broadcast address would thus be 10.128.240.15.
Software-defined networking technology is an approach to network management that enables dynamic, programmatically efficient network configuration in order to improve network performance and monitoring, making it more like cloud computing than traditional network management. SDN is meant to address the static architecture of traditional networks. SDN attempts to centralize network intelligence in one network component by disassociating the forwarding process of network packets, the data plane, from the routing process, the control plane. The control plane consists of one or more controllers, which are considered the brain of the SDN network, where the whole intelligence is incorporated. However, centralization has its own drawbacks when it comes to security, scalability, and elasticity, and this is the main issue of SDN.
Here's a diagram that may help you to understand software-defined networking better. Software-defined networking, or SDN, uses software-based controllers or application programming interfaces to create and manage a network via software. Conceptually, this differs from traditional networks as it uses software instead of dedicated hardware devices such as routers and switches to control network traffic. SDNs can create and control a virtual network or control a traditional hardware network via software. Software-defined networks are increasingly being used in large data centers for applications such as web servers. They can also be used to help organizations with managing their own data centers for storing large amounts of corporate data as well as running common applications used by the organization. In networking, the concept of a plane refers to where networking processes take place. There are two planes we are concerned with for a software-defined network: the control plane and the data plane. In a traditional network, the control plane is not centrally controlled but is distributed throughout the network devices such as routers and switches. In an SDN, the control plane is centralized. The control plane is where the network processes that direct the network traffic take place. The data plane is where the actual data traverses the network. An SDN has to be able to communicate with network devices where the data is found in order to program this data plane. This is done through what is referred to as the southbound interface. Through this interface, the network devices can be configured. The northbound interface is used by the network administrator to communicate with the SDN controller through a special application. Here is a diagram of a software-defined network comparing its organization to that of a computer operating system. At the top are the applications used by the administrator. The applications communicate with the controller just as the applications on a computer communicate with the operating system through the kernel. In turn, the SDN controller communicates with various network devices, just like the operating system kernel communicates with the various parts of the computer, such as the CPU, memory, and various devices. When looking for the appropriate solution to implement an SDN, there are 5 basic features you should check for. The first is cloud compatibility. The solution you decide on should be able to support applications hosted both on your premises as well as those hosted elsewhere, such as in the cloud. The SDN controller could and possibly should be hosted in the cloud as well. The second feature is integration readiness, which means that your controller needs to be able to connect with your applications, network devices, and tools that can be used for monitoring of your network. The third feature is data and analytics. One of the benefits of an SDN solution should be the ability for you to monitor and analyze the network to gain insight into the performance of your network. The fourth feature is programmability. This SDN solution should provide for an interface that will allow you to provide instructions or code to automate the various processes you will have it monitor. And the last feature is support, which, as with most IT technology, means that the vendor has a mechanism to provide advice and assistance when questions arise about the product. There are a number of SDN solutions on the market, many from well-known technology vendors. Some of these solutions include Cisco Meraki, Cisco Plus Network as a Service or NAAS, Cradlepoint NetCloud, and Dell SDN Solutions, as well as many others. For this lesson, there are 3 required videos which will help explain both subnetting and software-defined networking. There's also one optional video which presents a possibly faster way to determine your subnetting parameters. It is time now for our quick knowledge review. If I have a subnet mask of 255.255.255.192, how many networks or subnets can I have with how many hosts per network? 2 networks with 126 hosts in each? 4 networks with 62 hosts in each, 2 networks with 64 hosts in each, or 3 networks with 126 hosts in each? The answer is 4 networks with 62 hosts in each. You can determine this by looking at the subnet mask, which in binary looks like this. We can see that in the last octet we have 6 bits for the host. This means that there are 64 addresses for those 6 bits. But remember that host 0 is used for the network address, and the host with all ones is reserved for the broadcast address. Eliminating these 2 addresses from our possible list yields 62 possible hosts. Having 2 bits for the first bits in the octet being set to 1 means there are 4 possible networks with these bits set to 00, 01, 10, or 11. If I observe a CIDR notation for a network of 192.168.1.0/22, what would be the corresponding network mask? 255.255.0.0, 255.255.1.0, 255.255.252.0, or 255.255.254.0. The answer is 255.255.252.0. Remember that the /22 means that the subnet mask will have 22 bits and would thus look like this. What you now need to do is to convert these binary numbers to their decimal equivalent. The binary number 11111100 is 252 in decimal. Thus, our answer is 255.255.252.0. Which of the following is the term used to describe the interface through which the network devices in an SDN can be configured? The control plane interface, the network device interface, the northbound interface, or the southbound interface? The answer to this question is through the southbound interface. Which of the following were given as possible reasons for subnetting? Select all that apply. To improve network performance and speed, to reduce network congestion, to reduce the need for network security, to control network growth, or to ease administration. The answer is all of these were possible reasons for subnetting, except to reduce the need for network security. Subnetting will not reduce the need for security, but can in fact provide extra security by adding an extra level of security that an attacker would have to traverse in order to gain access to the systems and data within the subnet. This concludes Lesson 8 in Module 8. This also concludes Module 8.